being swapped in and out of the processor. Now, today we are looking at memory management because we said anytime a program is loaded or when you start any program or any process, then it is normally loaded into memory. That is where it would be operating from. And in order for this memory to be properly used, we need proper utilization of the memory. That is why we are looking at memory management. And here we are just looking at why it needs to be there. One of the reasons is to divide it so that it can accommodate as many processes as possible, or that it can accommodate as many programs. So that is one of the reasons why we do memory management, so that we can ensure it is properly utilized. So when we are looking at this utilization of memory, another reason is because the programmer or the user doesn't need to know where this program is located in memory. So the operating system will take over that functionality so that the programmer is not involved in whatever is happening in where the program is going to be located or where the process is executing from. So during the execution of the program, you may find that these processes are being swapped in and out of the disk to the main memory and taken back to the disk, depending on the activities that are taking place in the operating system or the activities that are being executed by the program. So that is why we need memory management. So number one is to properly utilize it. And number two is to ensure that the programmer doesn't need to know what is happening in the back end. It is the work of the operating system to be swapping processes in and out of the memory and taking them to whatever disk location they need to be. So when a program is normally loaded, we said that it creates a process control block. This process control block is the one which will contain all the information about that process, like which variables are being used, which data is being worked on, and instructions which are going to work on that data. And then after that, now it needs to contain all this information now, which is going to enable the process to be executed. So that is the main reason. So in order for this memory management to work, what are the requirements which need to be in place? One of them is protection. Now, when we are talking about protection, is the basic thing that we said that when a process is running, it is always allocated resources. Now, when it is allocated these resources, like the memory location or the data it is going to work on, then we have to ensure that that memory location it has been allocated, it cannot be accessed by any other process. That is what we mean by protection. Because when it is accessed by another process, it is being used by this current process, then we might have some collision. When that happens, then errors occur. And that is not good for our systems. So that is why we need protection. Then we also talk about it being impossible to check absolute addresses in programs. Here, that is what we are saying. To check in addresses in programs, because this program could be relocated or this process could be relocated. So if relocation takes place, it is the work of the operating system to ensure that this reference has also been relocated, so that any reference to this memory location can be also followed. That is what we mean. And that is one of the requirements, protection. Another memory management requirement is sharing. What do we mean by sharing? This is where now we are talking about allowing several processes to access the same portion of memory. How does this happen? If these processes are accessing the same data, we said that then it can be allowed. This memory location is containing information that can be accessed by these two processes. Then sharing, or the operating system, can now allow sharing. And this allows each process to access the same copy of the program rather than have their own separate copy of that program. That is what we mean by sharing. Another requirement for memory management is logical organization. And what we mean by logical organization is that there has to be some kind of procedure which is followed, or some set steps which are going to be followed when you are looking at memory. Programs are written in modules, and these modules can be compiled independently. And that is why we are talking about different degrees of protection which should be given to these memory modules, so that there is a level whereby you can only read that memory location, and there is a level where you can actually read and execute. So that is what we mean by logical organization. Logical organization, it means that some processes will access this memory and be able to read, or access it and be able to execute. And that is what we mean by logical organization. Another requirement is about physical organization. And here we are looking at the physical memory location. And we are saying that memory is available for a particular program and the data which that program is working on. Now, if this data is huge, or this data cannot be held in this particular memory location, then it means that you need another location where this data can be stored. And that is where now we bring about the concept of overlaying. Overlaying allows various modules to be assigned the same region of memory. So the programmer or the user or the program itself will not know how this location is available, but it is the work of the operating system to ensure that this region of memory can be shared among these programs, or among these modules of a program. So how is this memory organized? We can have what we call fixed partitioning. This was like old school method of memory organization, whereby this memory is divided into equal size partitions, and each of those partitions now can be assigned to a program. So any process whose size is less than equal then can be loaded. So for this process to be loaded into this particular memory partition, it has to be less than or equal to that particular partition. Now, if all the partitions are full, then the operating system has to be swapping a process out of that partition so that it can load another process. Now, a program may not fit in a partition. Now that is where the challenge comes in, and now the programmer must design a program with overlays. Of course, this had a challenge, and that is why I'm saying it is old school. Nowadays, it is not about equal size partitions, but dynamic memory allocation, which we will see. But there is this concept of fixed memory. But now the question comes in terms of, what about small programs? About small programs or processes? Then it means memory is being wasted because it is fixed in terms of its size. The partitions are fixed. That is why it is being wasted. And that is the reason why there is the need for a dynamic memory allocation. So here we are talking about the challenge being inefficient. The program, no matter how small, occupies an entire partition, and this is called internal fragmentation. That kind of wastage is called internal fragmentation, and that is what we need to deal with. This is an example of how that internal fragmentation takes place, because here we are talking about this is 8 megabytes, for example, and this operating system is going to divide these partitions into 8 megabytes, 8 megabytes. But now, if a process is like 4 megabytes, then it means some 4 megabytes is wasted. Again, another one is wasted. When there is a big memory requirement, then you have to do what we are calling overlay, which has a challenge. That is why now we start talking about placement algorithms with partitions, and here we are talking about equal size partitions, whereby all partitions are of equal size, and it does not matter which partition is being used. We also have an equal size partitions, whereby the operating system can assign each process to the smallest partition within which it will fit. And then you put a queue for each partition, so that once this process is done, then the next one, which is on the queue, can follow through. So processes are assigned in such a way that to minimize wasted memory within a partition. So that is a method which is trying to address this problem of fixed memory partitioning, and it is shown in this diagram. But then there is what we call dynamic partitioning, which now is currently being used for memories. And here we are saying partitions are of variable length or number, meaning that the size of the partition can increase depending on the requirement. So a process is allocated exactly as much memory as it requires, not the concept of fixed memory allocation, but you are given what you need. If a process requires 2 megabytes, it will be given 2 megabytes. If it requires like 10 megabytes, it will be allocated 10 megabytes. So this one is what we are now saying. It gets holes in the memory, and it is called external fragmentation, and we will see how this one is addressed. And here we are saying now the operating system must use compaction to shift processes so that they are contentious and all free memory is in one block. What we are saying in that is that when you are allocating this memory, like it is shown here, like here, the operating system is taking 8 megabytes, and we have like 56. So this is like 64 megabyte memory. So once it takes this portion of memory, this other one is available for allocation. And we are saying it is going to do dynamic allocation, whereby process 1 takes like 20 megabytes. So 36 is left. Process 2 takes like 14 and 22 is left. So, and it goes on like that until like 4 megabytes is left. So that is what we mean by dynamic partitioning. So let us see where does the external fragmentation come in so that it can be addressed here. And this is where we are talking about. So process 1 took 20, and then process 3 took 18, but now process 2 is already finished, and it has left like a gap here of 14 megabytes. What we are saying is that in order to remove this external fragmentation, what will happen now, the next process which comes next, which is process 4, will be allocated this remaining space. Before we go to this 4 megabytes which was left initially, we have to fill in this gap which has been left. So process 4 will take 8 megabytes here, and there is still 6 which is left. So if process 5 will come in, then it will have to be allocated here so that we deal with this problem of external fragmentation. And that is how it works. So the dynamic partitioning placement algorithms, they work like this. An operating system must decide which free block is available to allocate to a process. And we have said it grows chronologically, or filling with the available space after the space which has been taken by the operating system. And one of the algorithms, or one of the methods which is used, is this one we are calling the best fit algorithm, whereby it chooses the block that is closest to the size that is being requested. So you have to look into the memory like we have shown here. This process 4, it is required like 8 megabytes. So it can't fit in 4 megabits. So what happens is that it will take up the available space, which is like the 14 megabytes which was left. Now it is fit in there. That is what we mean by best fit algorithm, this one. So it is the worst performer because the smallest block is since the smallest block is found, then the smallest amount of fragmentation is left. And we have seen how that works. Here there is a fragment which is left, here there is a fragment which is left. That is why we are saying it is the worst performer overall because of those fragments which are left. But then we have the first fit algorithm. It is the fastest because it checks where the first available memory is and it fits the process there. So it may have many processes loaded in the front of memory that must be searched over when trying to find a free block. So you search through your memory and find which is the first available location. And that is where you fit your process. Then we also have another one, which we call the next fit algorithm. So here we are saying the operating system will allocate a block of memory at the end of the memory where the largest block is found. So the assumption is that at the end of the memory, that is where you will find the most space available. So in order for you to start searching, or the operating system will start searching from the end of the memory block so that it can find the largest available memory to fit that process. So the largest block of memory is broken down into smaller blocks, which now can be used for allocation. And then we are saying also in this one, compaction is required to obtain a large block at the end of the memory. So what will happen, the operating system will keep on refreshing so that it can check. That is periodically keep on checking the memory. If a process has finished operating, then what does it do? It does compaction. Compaction is just like pushing these processes towards one side so that available memory is left on the other side. And this is what is happening, what we are calling now the last allocated block. So first fit works like this. What is available at first? Best fit is what is available to fit our process, and then next fit looks at the end of the memory to see the most available memory so that it can allocate its process there. So that is how these algorithms work in dynamic memory partitioning. Then we also have the buddy system, is also another method whereby the entire space of memory which is available is treated as a single block of 2 raised to power u. And then if a request is made of size s for allocating to a process, that is 2 raised to u then minus 1, then s should be in between this one and 2 raised to power 2 to power u. That is, so the entire block is going to be allocated to this s as long as it fits between this value and this value. That is what it means. Or what we are basically saying is that if the operating system is being requested for a memory location which is of size s, what it will do is to look at its entire memory or what is available in the memory. Then it is going to be split into 2 blocks. That is why we are saying here it is going to be split into 2 equal buddies, or that available memory is broken down into 2 blocks, and then check, is this requested size able to fit in one of the blocks, or is it equal or less than to the blocks that have been split. And this process continues. If it is small, then you split again. And you continue splitting that memory until you get that space that is greater than or equal to S. And that is where you are going to allocate that memory. And this is how it works. So if you have this, what we are saying, this is 1 megabyte of memory. So request is for 100 kilobytes. So what do? You divide this into 2, 512, 512. Once you do that, 100K is still less. So what do? This 512, you're going to divide it again into 2. That is 256 and 256. Again, you see that 128 is left here, or the 256, this 256, you divide it again into 2, whereby you have 128 and 128, and then you see that the available now, the request for 100 kilobytes then is going to fit into 128, and that is where you are going to fit it. That is what we mean by a buddy system. So any questions so far? So this is the representation of a buddy system. You can look at it later. Then let us look at what we mean by memory relocation. So normally when a program is loaded into memory, then the actual or the absolute memory that is required has to be determined, because it is not like it is going to just lay in the entire memory or take up the whole memory. No, it has to be allocated a specific memory location. So when it is determined, or a process that is normally carried out, then a process is normally carried so that to ensure that this process is going to be in a particular memory partition. So when this memory partition has been given to a process, that location is normally locked or is made absolute to that process. And that is where it will be referenced during execution. Now, it will lay there, not unless it has been swapped out of the processor. It will lay there until processing is finished. If sometimes something happens, maybe it requires some kind of input-output. You remember those 5-step process we mentioned of the state? If it may require some input-output. So it may be swapped out of memory, or it may be swapped out of the processor. It means it may not even need to be in memory. So compaction will take place because it has been swapped out of memory. And that memory needs to be allocated to some other process which needs to work. So it will be swapped, compaction takes place, or clearing is done so that another process can take the available space. Once this is done, when it is loaded back into memory, it will occupy a different partition. And this means different absolute memory location. So that is where relocation comes in, because we are talking about compaction, and when it is loaded back into memory, it will go to another memory location. So that is why we need the concept of relocation, meaning that, yes, it was in the processor, it was being executed, but at some point, something happened. Maybe the processor wanted to do something else, what we talk about priorities, or this process needed some kind of input-output, so it needs to be swapped out. So compaction takes place. When it is being loaded, it will be relocated. That is why we are talking about now the program occupying a different memory location. And that is what we mean by relocation. This is a function which is carried out by the operating system. So that is where addressing comes in, because at any given time, this process will be given a specific address in the memory. Now, these addresses are of several types. Normally have a logical address, and this is a reference to a memory location independent of the current assignment of data to memory. And we are saying this has to be translated to a physical address. This is like a reference. What we are talking about is something, a logical address is like, yes, we have this data or this process in this and this particular location. But what we have put in memory is just a logical one or a pointer to the physical location. And that is why we are talking about translation. Then we have a relative address, whereby this address is expressed as a location relative to some point. Then we have the physical location, whereby this is the actual location in main memory. This logical reference could be an address which is stored somewhere in what we used to call the registers or the cache memory. So it will just be pointing. This is just a pointer showing that, yes, this is the address, but it is a reference, or it is showing a point to the actual location. That is why it is called logical, because it is not real. The real one is the physical location where this information, where this process or the data is stored, but it is pointed to by the logical address. And this is what we are showing here. So like we have the base register, these are the registers. So in main memory, we will have like in main memory, we have the real address or the physical address, but inside the registers, that is where we are just putting the logical addresses. But then the relative address is like a specific address from a specific reference point. Here we have an adder because and a comparator. All these, we are calling them relative addresses because they are in reference to the base register or to the bounds register. That is why we are calling them relative addresses. So, how do we use these registers during execution? When we are talking about the base register, that is the starting address for a particular process. A bounds register is the ending location of the process, and these values are set when the process is loaded and when the process is swapped in. Because we have said there is the aspect of swapping in and out of memory depending on what is happening with the processor. So at any given time, a process will be executed, but at some point it may be swapped out of the processor, so it is taken back to memory, and that is why we are talking about swapping. So the base register is the starting address of the process, and the ending address of the process is called the bounds register. So these registers are actually storing the addresses of these particular processes. And then the value of the base register is added to a relative address to produce an absolute address. The absolute address will be like what? The point at which the process has reached during execution. Either it was finished or it was swapped before it is finished. That is why it is called absolute. And it is relative to a particular address. Then the resulting address is compared with the value in the bounds register or at the point where it stopped or it ended. Now, in order for that to work, we normally use something called paging. Now, when we are talking about a page, is a chunk of a process. A process will be divided into threads. That is something we said. or a program during execution is normally divided into processes. And these processes will also have instances which we call threads. Now, several chunks of a process are the ones we are calling pages in terms of the memory allocation being given to them. That is why we are saying memory is going to be partitioned into small equal size chunks. And then those chunks of memory are going to be given into processes, or they are going to be assigned to particular processes. Those are the ones we call pages. That is, processes which have been assigned into memory chunks. Now, those chunks of memory are normally called frames. Now, the operating system is going to maintain a page table for each process. This table now is going to have several pages, or now what we are calling the chunks of the process. So they are going to be several pages, and each of them will contain the frame location for each page in the process and memory address consisting of a page number and an offset within that page. So this is how it will look like. The frame number is like the chunks which have been divided. So this main memory is going to be assigned to these processes. Like process A is going to have several chunks, or what we are calling pages now, 1, 2, 3, 4 of them. And then another process is going to be allocated several chunks as well. So that is how paging works. And they continue like that. So when we are saying these processes are being assigned to the memory, as much as we are saying a process has been assigned like memory location 0 up to 3, then inside it, there's going to be those chunks which are assigned. And this is how the page tables are going to be looking like. And then we have segmentation. Segmentation is whereby all segments of the program are going to be divided into segments, or all the parts of the program are going to be segmented, or they are going to be divided into small portions, and these portions are going to be given some length, and this length is divided into two parts. That is a segment number and an offset. Now, each offset is the one which shows the end of that particular segment before you move to the next one. And so segmentation is similar to dynamic partitioning. So we have at the higher level, this is what I want you to take home at the end of this. At the higher level, we have what we are calling partitioning for processes. And then these processes are also going to do segmentation, which is similar to dynamic partitioning. So that is how the operating system does memory management.